Las Vegas Strip, Times Square in New York, Shanghai, Tokyo. What do these apparently disparate cities have in common with one another? Probably a lot of things, but think about their nightlife. All of them are iconic for their bright, multicolored neon lights that beckon you into casinos, video arcades, movie theaters, or diners that they overhang. Have you ever looked at those and wondered, just how is that inviting glow accomplished on a chemical level? We owe the distinctive glow of what we commonly call neon lights, not just to neon, but to a small group of elements, each of which produces a slightly different colored glow when electrically excited inside the glass tubes that contain them. When excited by an electrical discharge, these gases illuminate and create the familiar light that bathes our favorite night spots in their glow. For example, tubes containing neon itself glow red when a voltage is applied to them, while tubes containing the element argon emit blue, and those containing krypton instead glow white. Now, mixtures of these and other gases can then be used to produce lamps that emit light of practically any color that we can imagine. So, what is it about different elements that causes them to glow in different colors when excited by this electricity? Well, the answer lies in the topic of today's lecture. It's a sophisticated dance of electrons through a highly structured system of orbits about the atom's nucleus. Rutherford was able to demonstrate that atoms consisted of dense, positively charged nuclei with sparse electron clouds around them. But the Rutherford model had those electrons awash in an undefined sea of space, held in place by simple electrostatic attraction. Each electron in his model is indistinguishable from the others, their only job being to balance the strong positive charge at the center of the atom. But electron clouds take on a structure far more complex than the Rutherford model would suggest. And it was shortly after the invention of those neon lights, in 1913 to be exact, that a Danish physicist by the name of Niels Bohr offered a theory about the atom that explained this phenomenon and took us one step closer to the modern understanding of the atomic structure. Bohr theorized that the electrons in atoms don't simply orbit random distances from the nucleus, but instead are constrained to more specific regions of space around it. He called these regions energy levels. Electrons could transition from one energy level to another, but could never lie in a stable orbit in between them. Essentially, Bohr argued that electron orbits are like steps on a ladder. As I climb the ladder, I input energy obtained from burning calories from my breakfast, and that energy becomes stored in the system as what we call potential energy. But my feet can only reside at specific, discrete distances from the ground, distances defined by the rungs of my ladder. If I were to try to rest my foot between any of those two levels, simply can't. So only certain discrete amounts of energy can be put into that system. Now let's think about the relative energy of each level again. But this time let's think about the energy released when I descend my ladder. I might fall by one rung, two rungs, or even all the way to the ground, but I can never fall a fraction of a rung for the same reason that I can never ascend by a fraction of a rung. Just as that ladder has discrete levels on which I can stand, the electron cloud of an atom also has discrete specific levels, in this case, orbits, in which an electron can reside. Use electricity or heat to move the electron into a higher energy orbit, and its potential energy increases. Allow that electron to fall down into a lower energy orbit, and its potential energy will decrease. But this time the energy is emitted not as heat, friction, sound, or broken bones as it would be with the latter example. This time that energy is emitted as a photon of light. So Rutherford was right that there was a dense positive core, a nucleus at the center of the atom. But his proposed structure of the atom left the electrons fairly unaccounted for, leaving them in sort of an amorphous orbit around that nucleus. But Bohr proposed something a little bit more sophisticated. Specifically, let's take a look at his model of a hydrogen atom to see what set Bohr's model apart. Now, a hydrogen atom will consist of one proton and one electron. And again, according to Rutherford, there was that proton at the center, and the electron simply moved around the outside with no particular place to be. But Bohr suggested that wasn't the case. Instead, Bohr suggested there was a discrete orbit associated with that electron. And when that electron was as close as possible to the nucleus, that was what we call the first energy level, its best possible orbit. However, if a little bit of energy is put into a hydrogen atom, it's possible to promote that electron to a higher energy level. So notice that the orbit here has gotten larger, and therefore the electron is farther away from the proton. So this would be a higher energy state. And he called this the second energy level. And again, by adding a bit more energy, he suggested that it's possible to promote that electron yet again to an even higher energy state. In this case, a third energy level. But that each of these energy levels is discrete. Just like the rungs of a ladder, it's impossible for the electron to be anywhere in between. It can only reside at the first, second, or third energy level or beyond. So why do we need to study this in the first place? Well, let's think about the relative energies of these different states of hydrogen atoms. Again, we have our lowest possible energy state over here on the left-hand side in the first energy level, and then the second, third, and fourth, each with a slightly higher energy. So if the N1 through N4 have increasing energies, that means that they are decreasingly stable as we move along. So we call this N=1 state the ground state of hydrogen because it's the most stable hydrogen atom that could possibly exist. And all of the other states that result from the promotion of that electron out of the ground state into a higher energy position are called excited states. Now, this is where Bohr's model becomes really remarkable, because it allows us to predict some of the properties of hydrogen using the energies associated with these transitions that we've just discussed. So let's bring back that hydrogen atom and take a look at it in terms of really quantifying the energy of those levels. So here's my hydrogen atom in its ground state, with the electron in the N=1 orbital. But remember, there are lots of other energy levels accessible, so let's put those in right now. I'm going to put in the first 6 for our discussion right now. Now, Rydberg's equation gives us a way to predict the wavelength of light that will be produced when an electron transitions from one energy level to the next. You'll notice down here I have an NF, meaning the final or the ultimate energy state in which the electron resides at the end of a process, and Ni, meaning the initial energy level of that electron. So, Rydberg's constant plugs into this equation and gives us the proportionality constant we need to determine the exact wavelength of light that will be emitted or absorbed in a transition. So let's look at a couple of examples here. Let's promote our electron all the way up to the 6th, 5th, 4th, and 3rd energy levels, and then allow it to fall to the 2nd energy level and see what kind of light is produced. So I can put a little bit of energy in to raise my electron up to the 3rd energy level. And now let's let it fall down to the 2nd. Rydberg's equation predicts that a red photon with a wavelength of 656 nanometers should be emitted. Now, if instead the electron falls from the 4th energy level to the 2nd, let's reset that. Here comes my electron. It falls. It emits another photon. But in this case, Rydberg's equation predicts that it will be a green photon with a wavelength of 486 nanometers. And if we go from 5 to 2, as you might imagine, it emits a photon of blue light. And from 6 to 2, a photon consisting of violet light. Now, all of these colors are in the visible spectrum, and so they're fairly easily observed. In fact, when we combine all of these transitions together in hydrogen atoms that are being excited either electrically or thermally, we get a spectrum. And that spectrum is unique to hydrogen. It allows us to determine the exact energy level differences in and among all of these orbitals of the hydrogen atom. This is what makes Rydberg's equation so remarkable. So electricity promotes an electron to a higher energy level in an atom, where it can then fall back downward, emitting light when it does so. But only in very specific defined packets of energy corresponding to very specific colors of light. But neon lights aren't the only way to observe this dance of electrons and among various energy levels. There's another very popular demonstration, and it's going to require the use of an open flame. So let's head into the lab for that. I'll see you there. I am beyond excited right now because I'm coming from Osmond Lab at Penn State University to show you some chemistry that we can't do in the studio or in our kitchens. As you can see, today I've got a Bunsen burner, I've got an open flame, so naturally I need to be in a safe place to do this. Now, what I'm going to do with this flame is I'm going to stimulate the metal ions contained in some solutions that I've created here that are flammable. So instead of using electricity as we did in neon lamps, we're going to use fire to stimulate these. Now, here's a solution that contains the element sodium. Now, you see a distinctive yellow color, one that most of us are very familiar with because sodium is in a lot of flammable materials that we see every day that burn. But let's change it up a little bit. Let's use the element potassium and see what happens. The flame has changed color. It's now a very distinctive violet. And how about copper? We'll use a solution of copper next. As you can see, when we burn the copper-containing solution, we get yet another color. We get a nice, pretty green. And finally, my personal favorite, lithium. And you can see lithium creates a beautiful red color. In fact, there's a little bit left on my burner there, coloring the burner's flame even now. So each of these elements created a distinctive color that we observe as just one color, but of course we really know that it's the result of many, many different electronic transitions happening within the unique electronic structures of these particular elements. So with little more than a flame and some solutions of simple metal chloride salts, we can observe the differences in color and emissions from different metal ions. Not the individual colors of their line spectra, of course. For that we would need an instrument. But our eyes see different colors because of the combined effect of those specific visible wavelengths being emitted. Proof of the existence of those line spectra. Bohr's model was a huge leap forward in understanding atomic structure. It was very, very close to the truth. Close, but just a bit too simple. Bohr's refinement to the model of the atom was to treat electrons like planets in a solar system, particles, occupying only certain orbits at certain distances around that central star. But there's one last refinement we have to make to get our model of the atom into the modern age. The final piece of the electron puzzle, and it was theorized by Erwin Schrödinger, an Austrian physicist. In the aftermath of Albert Einstein's groundbreaking theory about the duality of light, and de Broglie's revelation that duality extends to all matter, Schrödinger began to wonder, how might the wave nature of electrons dictate their behavior in atoms? When Schrödinger applied this concept to the structure of the atom, something amazing happened. He realized that electrons don't move in circular orbits the way a particle or planet might. Rather, they can occupy some very unusually shaped regions of space, regions that would have astronomers shaking their heads, but they make perfect sense when you think of electrons as waves. Although this theory was a departure from the idea that electrons followed circular orbits around the nucleus, Bohr's original ideas and the similarities to the orbits of physical objects have led chemists to dub these regions of space occupied by electrons orbitals. So, as chemists, we're tasked with characterizing these orbitals, each of which is distinct from all others in a given atom in one way or another. Exactly which orbitals do or do not contain electrons in an atom can give that atom many of its properties. So we need to come up with an address for each and every electron in the atom so that we can discuss just one of those electrons or one type of those electrons when it is warranted. To accomplish this requires that we convey 4 distinct properties of the orbiting electron: its orbital's size, its orbital shape, and its orbital's orientation, and also a special property of the electron itself, known as magnetic spin. The first of these properties is the size of the orbital, which is indicated by the principal energy level. For example, orbitals in the first principal energy level are generally smaller than those in the second energy level, which are themselves smaller than those in the third. The next is the shape of the orbital. We indicate orbital shapes referring to what we call a subshell. Now, each principal energy level has a certain number of subshells. It's equal to the principal number. For example, if the first principal energy level is looked at, it only has one subshell. The second principal energy level will have two subshells. The third principal energy level will have three, and so on. The first subshell of any level is called the S subshell. S subshells are spherical, so they contain only one orbital each. The second subshell is called the P subshell, and it actually contains three orbitals. They're shaped something like a dumbbell centered about the nucleus. The third subshell contains 5 d orbitals of even more complex geometries, and the fourth subshell contains 7 f orbitals, whose geometries are truly perplexing to the uninitiated. Nevertheless, because each orbital within a specific subshell has similar shape and size, electrons that occupy them will have the same energy. We call sets of orbitals with the same energy degenerate orbitals. That's not meant to be an insult. It comes from a less commonly used definition of the term, meaning a lack of distinctness in structure or order. Now we're on to our third property, the orientation of the orbital. Of course, we can easily see why there's only one s orbital per energy level. This is because a sphere centered on the nucleus can only have one orientation. But the p subshell is different. It contains 3 dumbbell-shaped orbitals, and each orbital has its own axis, which is arranged perpendicular to the other 2, like the axes in a Cartesian coordinate plane. So we often refer to these as px, py, and pz orbitals in reference to those axes. Just like their geometries, the designations of d and f orbitals get a bit complicated, and we'll be spending most of our time in this course focusing on the effect of s and p orbitals on the behavior of atoms. So, in the interest of simplicity, we'll just put those into the complicated bin of orbital geometries and orientations. So, we've now seen 3 of the 4 important properties of an electron orbiting an atom. The size of its orbital indicated by the principal energy level, the shape of its orbital indicated by the subshell designation, and the orientation of that orbital. The final parameter that we have to consider is a bit tougher to understand. It's a magnetic property of the electron itself that we call electron spin. Any electron in an atom can have one of 2 magnetic alignments. Physicists call these 2 alignments spin up and spin down. Sometimes you might see them written as +1/2 and -1/2 as well. This is easily envisioned if you've ever held 2 bar magnets close together. Align the magnetic poles parallel, and the magnets will repel one another. But turn one over and align them anti-parallel, and they're attracted. So we can think of electron spins in the same way. A parallel alignment of electron spins will cause a repulsion between those 2 electrons, but an anti-parallel alignment will create an attraction. It's because of this magnetic spin that 2 electrons can occupy the same orbital. You see, electrons usually like to have their space. They push against one another because they have like charges, and packing 2 negatively charged particles in the same orbital, well, that creates a repulsive force, which makes it energetically unfavorable. But in certain situations, electrons of opposing spin can share an orbital when there's no place else for them to go. This attractive force of their spins doesn't fully cancel out their electrostatic repulsion, but it does reduce it somewhat. So electrons often occupy orbitals in pairs, but only when one electron is spin up and another one is spin down. So Bohr's idea that the electrons have specific orbits, and Schrödinger's idea that those orbits are a result of their wave properties, have led us to an understanding of how electrons arrange themselves around an atom's nucleus. The location of a given electron in an atom can be defined by the size, shape, and orientation of its orbital, as well as its magnetic spin. But this means that each electron in the cloud of an atom is unique. If we want to have a discussion about how one particular electron in an atom behaves, and we very often do, then we need a way of clearly describing exactly which electron we're talking about and exactly where it can be found. Building on his quantum mechanical model, Schrödinger was able to calculate the size, shape, and orientation of orbitals, as well as the electron spins for simple atoms like hydrogen. Each electron has its own home in space around a nucleus, not unlike each of you viewing this course has your own unique home somewhere in the world. So let's think about that for a moment. When we need to send a letter or pay a visit to a particular place in the world, we need to know the exact location. So to communicate that location to the postman or the taxi driver, what kind of information do we need? Of course, we need an address. And that is exactly what Schrödinger proposed. His system works much like a geographic address, which contains multiple pieces of information like state, city, street, and house number. As long as at least one of our 4 address components is different, then the location that it represents must also be different. For example, 1 Schrödinger Street in Boersville isn't the same place as 2 Schrödinger Street in Boersville. Nor is 1 Rutherford Street in the town of Boersville, or 1 Schrödinger Street in the town of Rutherford. As long as one component of those addresses is different, so is the location that it indicates. The same is true of electrons. Within a given atom or ion, all electrons must have their own unique address. But how do we convey this so-called address? Schrödinger came up with a simple system using numbers to represent those 4 properties of orbital size, shape, and orientation, and electron spin. It works just like a physical address. He called these numbers quantum numbers, and they give us a rapid way to describe exactly which electron we want to call attention to. The first of these is size, which is represented by the principal quantum number n. N begins with 1 for the first principal level, 2 for the second, and so on. Next is the shape of the orbital, or the subshell to which it belongs. This is defined by what we call the azimuthal quantum number. In this case, a 0 represents an S subshell, 1 represents P, 2 for D, and so on. Next comes the orientation of the orbital, which we represent with the magnetic quantum number. This number can be any integer between negative L and positive L for a given subshell, so it's dependent on the azimuthal quantum number. In other words, S subshells can only have one orbital with a magnetic number of 0. P subshells with an azimuthal number of 1 can have magnetic numbers of -1, 0, or 1. This makes sense, right? 3 orbitals in a P subshell. Continuing on, D subshells can be -2, -1, 0, +1, or +2, representing the 5 d orbitals in any D subshell, and so on. Finally, we have the spin quantum number, which indicates the magnetic spin of a given electron. Here, we use -1/2 or +1/2 to indicate the spin up and spin down configurations. Using this quick notation, a spin-up electron in a 3s orbital becomes n equals 3, L equals 0, m equals 0, s equals +1/2. An electron sharing that orbital with our previous electron would be n equals 3, L equals 0, m equals 0, s equals -1/2. So Schrödinger's system of quantum numbers gives us a way to refer to a single, specific electron within an atom, facilitating the discussion about the electronic structure of those atoms. So now we've been introduced to the basics of energy levels and orbitals in atoms and the electrons that occupy them. That means that electrons have a lot of choices. Each atom has literally dozens of available atomic orbitals into which its electrons can go. So where can we expect to find the electrons in any given atom? Well, most often we discuss the electronic structure of atoms in what we call the ground state, or the most stable arrangement of electrons possible. Those neon atoms in our lights and the metal ions in our lab solutions are all in this ground state when no energy is being applied to promote them. So let's think about that ground state. Let's pretend that we have an atom with no electrons in its cloud, and our job is to fill that cloud with electrons in the ground state configuration. When we limit our discussion to the ground state of an atom, electrons fill atomic orbitals in a very predictable way. And in order to do this, we'll need to first set 3 important rules for filling orbitals within that electron cloud. First, there is a very specific filling order of orbitals in an electron cloud. We call this order the Aufbau order, from the German word meaning building up. Next, we have the Pauli exclusion principle, which states that no two electrons can have the exact same orbital address and spin state. In other words, no two electrons in the same atom can have the same 4 quantum numbers. Remember that when we start allowing two different places to have exactly the same address, our whole system would break down, right? Now finally, we have Hund's rule. Hund's rule states that electrons will maximize their spin. And when keeping in line with the Aufbau order and Pauli exclusion principle, what this means is that electrons will spread out within a given subshell, placing one electron with similar spin into each degenerate orbital before any electron in that subshell is paired up. Just remember that electrons like their space, and given the option to have an orbital of the same energy all to themselves, they're going to take that orbital. Just like the state, city, street, and house number allowed us to unambiguously define a location on our map, we need to quickly and easily define the energy level, subshell, specific orbital, and spin state of an electron to define its location in that electron cloud. So as chemists, if we want to understand how excited atoms decay as they do when they produce light in a neon lamp, we need to characterize the relative energies of these orbitals. And that means considering the energies of all 4 parts of the electronic address. So let's now consider not just the size, shape, and orientation of different atomic orbitals, but the energies of these orbitals as well. We need to do this because we know that whenever possible, electrons will seek out the lowest energy orbitals in search of an atom's ground state. So Schrödinger had introduced a whole nother wrinkle into the calculation. Bohr's model was just too simple. It works well for a hydrogen atom in which we have one electron orbiting one proton and just a few energy levels accessible. But things got more complicated when Schrödinger came to bear on the equation. So these are all of the energy levels accessible to an actual hydrogen atom, based upon Schrödinger's calculations. You'll notice that there are sublevels of S, P, D, and F, all of which combine to make overall energy levels 1, 2, 3, 4, 5, 6, and even 7. Now notice that the 1s is pretty simple here, it's just 1. Then there's a 2s and a 2p, and as I increase, each time I step up, I get more and more available sublevels. Of course, the 6th and 7th theoretically have many, many, many sublevels, but we have yet to discover any atoms large enough to have electrons that populate them. So we usually cut off the diagram right about here. But notice that when I arrange all of these subshells in order of energy, that they don't line up numerically. That we go from 1 to 2 to 3 to 4, but then have to hop back to 3, then into 4 and 5, then back to 4 again. The order can seem a little bit confusing, but it's actually very systematic. And we have a name for this. It's called the Aufbau order, from Aufbau meaning to build up. So anytime we want to determine the ground state electron configuration of an atom, we simply take the number of electrons we know to be in the cloud of that atom and use them to fill the Aufbau order. Now, not only that, remember, we can use the Pauli exclusion principle, which tells us that no two electrons in the atom can have the same 4 quantum numbers, and Hund's rule, which tells us that we have to maximize spin whenever possible, and actually determine exactly where and how all of the electrons in a ground state atom are configured and located. Let's do that for the first few atoms of the periodic table. For example, hydrogen. Well, we know hydrogen has 1 electron. So naturally, that would be in the 1s orbital in a ground state hydrogen atom. Increasing 1 to helium means we put a second electron in the 1s, right? Not quite. Notice my electrons have the same spin state, which means they have the same 4 quantum numbers. And that is a violation of the Pauli exclusion principle. So I have to place my second electron in, spin down, to be sure that I satisfy that requirement. Now let's move on. Let's take a look at lithium. Adding a third electron, I begin to populate the 2s subshell. Adding another electron takes me up to beryllium and fills the 2s, being sure the electron is spin down. If we continue to look at boron, we now place an electron into the 2p subshell. Going 1 higher, I have another electron. What do you think? Well, the Pauli exclusion principle is satisfied, right? But in this case, Hund's rule is not, because I had to put that electron spin down in order to pair it. Whereas by putting it into its very own orbital, I can get around that. Can't be spin down though, remember that's a violation of Hund's rule. Has to be spin up. So I've maximized spin by having the two unpaired electrons both spinning the same way. And again, we add another electron, spin up. Now I can start pairing. As I go, again, I put my next electron in spin down and finish off my 2p by adding two more electrons. That gets me all the way up to neon. This is the ground state configuration of a neon atom. And as I continue going across the periodic table, building my atoms up larger and larger, their ground states continue to fill, following all three of these very critical rules: the Aufbau order, the Pauli exclusion principle, and Hund's rule. Very soon, we're going to see how the electron configurations of atoms also allow us to predict certain properties, such as the relative stability of elements, their ionization properties, bonding behavior, magnetic properties, and more. But for now, it's time to summarize the lesson. That was quite a lecture. Let's think about what we've accomplished here. We've discussed how the Bohr model of the atom was the first to propose that not all electrons within an atom's electron cloud are equal. And we saw how Rydberg was able to mathematically model the energetics of different electron orbits in isolated hydrogen atoms, successfully explaining its line emission spectrum and touching off a century of discovery with respect to the electronic structure of atoms. We then discussed the modern view of the electron cloud. We saw how the size, shape, and orientation of an electron's orbit in conjunction with the electron's magnetic spin make every single electron in an atom distinct from all others in that atom. Then we took a deep look at how the energy of different orbitals dictates the filling of the electron cloud based on the Aufbau order. And we saw how Hund's rule and the Pauli exclusion principle combine with the Aufbau order to allow us to predict the exact location and spin state of all electrons within a neutral atom in its ground state. We're rapidly closing in on our first course goal, that of understanding the properties of atoms and the elements that they comprise. Next time, we're going to conclude this task as we take a look at how these electron configurations help us to explain and predict properties of similar elements using the periodic table.